Look up at the night sky. It's a tapestry of distant stars, planets, and galaxies. A universe that began from unimaginable density and temperature. This is the story of the universe's birth, from the Big Bang to the first starlight. The Big Bang describes the universe's large-scale evolution. Imagine all of space and time compressed into a point smaller than an atom. Then, in a sudden burst, the universe was born. The Big Bang model is supported by a wealth of observational evidence. One compelling piece of evidence is the redshift of distant galaxies. Just like the sound of a siren drops in pitch as it moves away, light from distant galaxies stretches, shifting towards the red end of the spectrum. This redshift indicates that the universe is expanding. Another key piece of evidence is the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation, discovered in 1965, provides a snapshot of the universe as it was just 380,000 years after the Big Bang. The Big Bang wasn't a chaotic explosion, but rather a process governed by physical laws. As the universe expanded and cooled, energy began to condense into matter, following Einstein's famous equation E=mc². This marked the beginning of a remarkable transformation. In the earliest moments after the Big Bang, the universe was an inferno of unimaginable heat and density. It was during this epoch, a period known as the Planck epoch, that the fundamental forces of nature were unified. The Planck epoch represents the very edge of our understanding of the universe. It lasted for an incredibly short period, from time 0 to approximately 10 to the power of -43 seconds. During this epoch, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are thought to have been unified into a single force. Our current theories of physics, such as general relativity and quantum mechanics, break down at the Planck scale. To understand this epoch, we need a theory of quantum gravity, a theory that can reconcile the large-scale structure of the universe with the strange world of quantum mechanics. As the universe expanded, it cooled. This cooling led to a cascade of events that shaped the early universe. One of the most significant events was the separation of the fundamental forces. First, gravity separated from the other forces, followed by the strong nuclear force. This separation of forces had profound consequences, setting the stage for the formation of the first particles and the eventual emergence of stars and galaxies. As the universe continued to cool, a pivotal transition occurred. The universe became transparent to light. Prior to this point, the universe was a hot, dense soup of particles, and light couldn't travel freely. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and neutrons, forming the first atoms. This event, known as recombination, marked a turning point. With the formation of neutral atoms, the universe became transparent to light. Photons, the particles that make up light, were finally able to travel freely through space. This light, which has been traveling through the universe for billions of years, is what we observe today as the cosmic microwave background radiation. The cosmic microwave background radiation provides a glimpse into the early universe, revealing subtle temperature fluctuations that would later give rise to the large-scale structure of the cosmos. It's a testament to the incredible journey the universe has undertaken. Section 5. The first elements, building blocks of the cosmos. During the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur. Protons and neutrons collided and fused, forming the nuclei of the lightest elements, hydrogen and helium. This process, known as Big Bang nucleosynthesis, produced the primordial abundance of elements that we observe in the universe today. Hydrogen, the simplest and most abundant element, would go on to play a crucial role in the formation of stars. Helium, the second most abundant element, would also contribute to the evolution of stars and galaxies. The formation of hydrogen and helium marked a crucial step in the evolution of the universe. These elements, forged in the heat of the Big Bang, provided the raw materials for the formation of stars, galaxies, and ultimately, life itself. However, the universe was still a far cry from the star-studded cosmos we observe today. It would take millions of years for the first stars to ignite, illuminating the vast expanse of space. Section 6. From Chaos to Order. The formation of cosmic structures. After the formation of hydrogen and helium, the universe entered a period known as the Dark Ages. During this time, the universe was filled with a diffuse gas, primarily hydrogen and helium, and no stars had yet formed. However, gravity was at work, slowly drawing matter together. Over millions of years, tiny fluctuations in the density of the early universe, amplified by gravity, grew into larger and larger structures. These regions of higher density became the seeds of galaxies, massive collections of stars, gas, and dust held together by gravity. Within these galaxies, smaller clumps of gas began to collapse under their own gravity, forming the first star clusters. The formation of galaxies and star clusters marked a turning point in the evolution of the universe. It was within these cosmic structures that the first stars would ignite, bringing light to the darkness. Section 7. The Cosmic Dawn. The first stars ignite. Deep within the dense clouds of hydrogen and helium, gravity continued to draw matter inward. As the gas clouds collapsed, they heated up, reaching temperatures and pressures high enough to ignite nuclear fusion in their cores. This marked the birth of the first stars. These first stars were unlike any stars we observe today. They were massive, hundreds of times more massive than our sun, and incredibly luminous. They burned hot and fast, exhausting their nuclear fuel in just a few million years. The intense radiation from these first stars ionized the surrounding hydrogen gas, stripping electrons from atoms. This process, known as ionization, gradually transformed the universe from a neutral state back into an ionized plasma. The first stars played a pivotal role in the evolution of the universe. They synthesized heavier elements in their cores, elements that would eventually become the building blocks of planets and life itself. Section 8. Observing the Distant Past. Telescopes as time machines. Looking out into the vastness of space is like looking back in time. The light from distant objects, whether stars or galaxies, takes time to reach us. The farther away an object is, the longer it takes for its light to reach us, and the further back in time we are looking. Astronomers use powerful telescopes, both on Earth and in space, to observe the most distant objects in the universe. These telescopes act as time machines, allowing us to study the early universe and the formation of the first stars and galaxies. The Hubble Space Telescope, launched in 1990, has revolutionized our understanding of the early universe. Its observations have provided stunning images of distant galaxies and have helped astronomers estimate the age of the universe. The James Webb Space Telescope, launched in 2021, is even more powerful than Hubble. It is designed to observe the universe in infrared light, which can penetrate clouds of gas and dust, allowing us to see even further back in time. Section 9. A universe still unfolding. The story of the universe, from the Big Bang to the first stars, is a tale of incredible transformations. It's a story of expansion, cooling, and the emergence of complexity from simplicity. The universe is still expanding, and galaxies are still evolving. New stars are being born, while others end their lives in spectacular supernova explosions. The quest to understand the universe is a journey without end.